We have a variety of things that we want to find out about this circuit, but I want to focus in on part C here. We want the complex power delivered by the source. In order to get that, I'm going to need the current out of the source in phasor form. Then S will be equal to the voltage phasor times the complex conjugate of the current phasor over 2. In order to find this current phasor, I have a variety of approaches I can use. This circuit's reducible. I can combine these two in series. Those are in parallel with this, which is finally in series with 3 ohms. So if I get equivalent impedance, ZEQ, I can use circuit reduction, and then I will be equal to the given voltage phasor over the equivalent impedance. Other possible approaches for how I might be able to find this would be nodal analysis. If I use that approach, I could choose a reference node down here, then this and this would be independent nodes, this would be a dependent node. That would give me 2 equations and 2 unknowns. And then the current I would be this voltage minus this voltage over this 3 ohm resistance. I could also use mesh analysis. If I did that, I'd have 2 mesh loops. This would be, say, mesh current I1. This would be mesh current I2. So I still have 2 equations, 2 unknowns. This current I would just be the same as I1, so I wouldn't have to solve another equation in order to get the current after I'm done. It'd be a little bit easier, but I think circuit reduction is probably going to be my easiest approach. Getting I by whatever approach, circuit reduction, nodal analysis, or mesh analysis, is part B. I've decided that that's probably easily done using circuit reduction, so I need the equivalent impedance seen by the source, which is part A. So basically, in parts A, B, and C, I'm walking you through what I think is a logical process to get the complex power. If I just come out and ask you for the complex power without asking for anything else, you would still need to go through this thought process, know that you need the current out of the source, pick a reasonable approach towards finding that current, and then do that one. At any rate, this is going to be a frequency domain problem. Complex power is fundamentally an AC thing, so we need the frequency domain circuit. Let's go to the next slide and do our problem. So here's our frequency domain circuit. I've converted all of the circuit elements into their equivalent impedances. Now I can start doing combinations to get ZEQ. So what I want is this impedance seen by the source. These 2 elements are in series, so this equivalent impedance is just the sum of the 2 individual impedances. So this is minus J3 plus J ohms, which is equal to minus J2 ohms. That impedance is then in parallel with this J3 ohm impedance. So this equivalent impedance, ZEQ2, is going to be the product of the 2 minus J2 ohms times J3 ohms over the sum of the 2 minus J2 ohms plus J3 ohms. Let's see, this is going to be 6 over J. If I move J into the numerator, that changes the sign, so this is going to be minus J6 ohms. Now this whole impedance is in series with the 3 ohm resistor, so the equivalent impedance seen by the source, ZEQ, is going to be the sum of the 3 ohm resistor plus the negative J6 ohm impedance, 3 minus J6 ohms. That's actually the solution to part A. Part B is to find the current out of the source, I. I is going to be the voltage, 2 at an angle of minus 25 degrees over the equivalent impedance, 3 minus J6 ohms. Converting this to polar notation becomes 2 at an angle of minus 25 degrees over 3 times the square root of 5 at an angle of minus 63.4 degrees. So the current phasor is 2 over 3 times the square root of 5 at an angle of minus 25 minus a minus 63.4 is positive 38.4 degrees. The current out of the source, I of t, is going to be 2 over 3 square root of 5 cosine of the frequency, 3t, plus 38.4 degrees. And that's my answer for part B. Part C, I need the complex power. S is a voltage phasor, V, times the complex conjugate of the current over 2. So substituting in my numbers, V is 2 at an angle of minus 25 degrees. The current magnitude is 2 over 3 square root of 5 at a phase angle of 38.4. Taking the complex conjugate changes the sign on the angle over 2. That 2 cancels with that 2, so this becomes 2 over 3 square root of 5 at an angle of negative 63.4. And there's my answer for part C. In part D, I want the power dissipated by this 3 ohm resistor. And I have a trick I can pull here. The only resistor in this circuit is this 3 ohm resistor. So any average or real power in the circuit will be dissipated by that 3 ohm resistor. So I can just take the real part of S. That gives me the power dissipated by all of the resistors in the circuit. Since there's only one resistor, that will give me the power dissipated by that resistor. So this is just the magnitude, 2 over 3 square root of 5, cosine of this phase angle minus 63.4. That turns out to be 0.133 watts. As usual, there's more than one way to do anything, so if you didn't happen to notice that this is the only resistor in the circuit, you can still find this pretty easily from the current. Let's make a little room. So an alternate approach to part D, we know that the power of a resistor, P3 ohms, is just going to be the RMS current squared times the resistance. So this is going to be the current, which we already found. It's I. 2 over the 3 square root of 5. The RMS value is 1 over root 2 times that magnitude. Square that, multiply it by 3 ohms. That cancels with that. We have root 2 over 3 square root of 5 squared times 3, which is 2 over 9 times 5 times 3, which is 2 over 45 times 3. I can factor out a 3. That's 2 over 15 watts, which is the same answer as that if I do the arithmetic and divide 2 by 15.